Ever wondered how text editors like Google Docs can highlight the longest run of nearly identical characters, even if you're allowed to make a few mistakes? That's the magic behind LeetCode's longest substring without repeating characters, a pattern mastery 100 essential and a frequent favorite in Facebook and Google interviews. This problem is the ultimate test of sliding window mastery. Let's use the basic approach: break down, assess, structure, implement, check, to get clarity and confidence. You're given a string and an integer k. Your task? Find the length of the longest substring you can get by replacing at most k characters so that all the characters in the substring are the same. For example, in AABABBA with k equals 1, you can replace 1b to get AAABBA or AABAAA, making a substring of length 4. Edge cases. Strings with all the same characters, k greater than the string's length, or an empty string. Suppose you're building a DNA sequence analyzer. To identify mutation-prone regions, you want to know the longest segment that could be made uniform by changing at most k bases. A brute force approach would try every substring, making replacements. This is O(n cubed), which won't work for long inputs. The optimal strategy is a sliding window. Keep track of character frequencies in the window. The minimum number of replacements needed is window length, count of most frequent character. If this is less than or equal to k, we're good. Otherwise, we shrink the window from the left. This ensures O(n) time, since both pointers only ever move forward. Here's our game plan. Use a hash map or array to track the frequency of each character in the current window. Use 2 pointers, left and right, for the sliding window. For each step, expand the window by moving right. Update the count of the most frequent character in the window. If the window needs more than k replacements, shrink from the left. Track and update the maximum window length throughout. Return the max found. We start by defining a class called solution. This is just the container where our algorithm for the character replacement problem will live. Here we define the method character replacement. It takes a string s and an integer k, which represents the maximum number of characters we're allowed to replace. The method will return the length of the longest substring we can make where all characters are the same, after doing at most k replacements. We create an integer array count of size 26. Each index represents a capital letter from A to Z. As our window slides over the string, count x will store how many times a particular character appears inside the current window. It's like having 26 counters, one for each letter. We declare max count to track the highest frequency of any single character within our current window. This tells us what letter is currently dominant in the window, useful for understanding how many replacements we'd need. We create max length to keep track of the longest valid window we've seen so far. That's the answer we'll eventually return. We set L to 0. This is the left pointer of our sliding window. As the window grows and shrinks, L will move to the right when we need to tighten the window. Now we start a loop with R as the right pointer of the window. It runs from 0 up to the end of the string. At each step, the window is defined by the range, L, R. Time complexity note: this for loop moves are from left to right once, and as we'll see, L also only moves forward, so the whole algorithm runs in O(n) time, where n is the length of s. Inside the loop, we grab the character at position R using s.char at R. We subtract A to convert it into a 0 to 25 index, then increment the corresponding count value. For example, if the character is C, s.char at R, A gives 2, so we increment count 2. This updates our frequency table for the current window. Here we update max count. We compare the existing max count with the new count of the current character and keep the larger one. This means max count always reflects the highest frequency of any single character in the current window. That's crucial to knowing how many replacements we need to make all characters match that most frequent one. This comment explains the logic that's about to happen. If the current window requires more than k character changes to become all the same letter, we need to shrink the window from the left. This while loop checks if our current window, L, R, is invalid. R, L plus 1, is the size of the window. Max count is the count of the most frequent character inside the window. The difference, R, L plus 1, max count is how many characters we'd need to change to make all characters match the most frequent one. If that number is greater than k, we're trying to change more characters than we're allowed, so the window is too big and we must shrink it from the left. Inside the while loop, we adjust our frequency table because we're about to move the left pointer. We look at the character at position L and decrement its count in the count array. This is like saying, this character is no longer part of the window. Then we move the left pointer L one step to the right, effectively shrinking the window. We keep doing this until the window satisfies the condition that it can be fixed with at most k replacements. This closes the while loop. At this point, the window, L, R, is valid. It either already has all identical characters or can be made so with at most k replacements. Now we update max length. We compute the current window size R, L plus 1 and compare it with our best result so far. If the current window is longer and still valid, we store its length in max length. This keeps track of the longest valid substring we've seen as we slide. This closes the for loop. We've now expanded and shrunk the window across the entire string, always maintaining the best possible answer. Finally, we return max length, which represents the length of the longest substring we can get by replacing at most k characters so that all characters in that substring are the same. Space complexity note. We use an array of size 26 and a few integers, so the extra space is 01, constant, independent of the input length. This closes the character replacement method, and this closes the solution class. And that's how this algorithm works. It first sets up a sliding window with frequency tracking for characters, then expands and shrinks that window to ensure we never exceed k allowed replacements while updating the best window length. Efficient, simple, and elegant. Now let's run this test case. Here, s equals AB is our input string, and k equals 2 means we're allowed to change at most 2 characters in the string to any other uppercase letter, in order to create the longest possible substring where all characters are the same. In ABAB, we have 2 A's and 2 B's. If we focus on A as our target character, we can change the 2 B's to as using our 2 allowed operations, turning the whole string into AAAA. That gives us a substring of length 4 with all identical characters. Similarly, if we chose B instead, we could turn both A's into B's and still get BBB, again length 4. Our sliding window logic tracks the window size and the count of the most frequent character in that window. As long as window_length, max_freq less than equals k. We know we can make the entire window the same character width at most k replacements. For the full window ABOB, window_length equals 4, max_freq equals 2, so 4 to 2 equals 2, which is exactly k. So the entire string is valid, and the program returns 4, perfectly matching the expected output 4. So, our implementation is correct. The algorithm successfully finds the longest substring that can be turned into repeating characters using at most k replacements, efficient and accurate. We start by defining a class called solution. This is just the container where our method will live. This method character replacement takes a string s and an integer k, and it returns the length of the longest substring you can get by changing at most k characters so that all characters in that substring are the same. Here we store the length of the string s in n. This makes it easy to reuse the length without calling s.length multiple times. We create a variable max length to keep track of the best, largest, valid substring length we've found so far. This loop goes through every uppercase letter from A to Z. For each target letter, we'll pretend. What if I want the substring to be all this letter? Since there are always only 26 letters, this outer loop is effectively constant. It adds a fixed factor, so the time complexity stays O(n) overall when combined with the inner sliding window. For each chosen target letter, we reset 2 things. L is our left pointer of the sliding window. Replacements counts how many characters inside the current window are not equal to target, i.e., how many characters we'd need to change. Now we start the inner loop with R as the right pointer of our sliding window. We'll expand the window 1 character at a time, from left to right across the string. This loop visits each character once per target, so it's O(n) for each target, giving overall O26n, equals O(n) time. At each step, we look at the character at position R. If it's not equal to our current target, we increase replacements because this is a character we'd need to change to make the whole window all target characters. This while loop checks if we've exceeded our allowed number of changes, k if replacements is greater than k, our current window is not valid anymore and we need to shrink it from the left. As we move the left pointer L forward, we check the character that's leaving the window. If that character wasn't equal to target, then it was contributing to our replacements count, so we subtract 1 because it's no longer inside the window. Then we slide the left pointer to the right by 1 position, effectively shrinking the window from the left until the window becomes valid again, meaning replacements less than equals k. Closing the while loop that keeps our window within the allowed number of replacements. Here we update max length with the size of the current valid window. The length of the window is R, L plus 1, and we keep the maximum overall windows we see. This is a quick O(1) operation inside the loop. We've now finished scanning the entire string for this particular target character. We've tried every target letter from A to Z, so by now max length holds the best possible answer across all characters. Finally, we return max length, which is the length of the longest substring that can be turned into all the same character using at most k replacements. Closing the character replacement method. And closing the solution class. And that's how this algorithm works. It first tries every possible target letter from A to Z and sets up a sliding window, then adjusts that window while counting how many characters need replacing, always tracking the longest valid window. Efficient, simple, and elegant. Let's test our function using this input, the string AABABBA and k equals 1. Here, the string represents a series of characters, and k tells us how many characters we're allowed to replace so that we can form the longest substring of the same repeating letter. Here's why the solution works. Our algorithm uses a sliding window to track a range of characters and counts how many times each letter appears in that window. We always keep track of the most frequent character in the current window. As long as window length, max frequency less than equals k, we know we can turn the whole window into the same letter with at most k replacements. For example, one of the best windows is AABA. In AABA, the letter A appears 3 times and B appears once. With k equals 1, we can replace that single B with A, turning it into AAA, a length 4 substring of repeating characters. No other window in the string can give us a longer valid substring under the same rule, so the answer is 4. And that's exactly what our program outputs, 4. This matches the expected result and confirms that our sliding window and frequency tracking logic is working correctly for this test case. So, our implementation is correct. The algorithm successfully finds the length of the longest substring that can be turned into repeating characters with at most k replacements, efficient, accurate, and reliable. Alright, let's wrap it up. The longest repeating character replacement problem is one of those elegant sliding window challenges that tests how well you can balance flexibility and precision, just like optimizing text or DNA analysis in real time. We began by understanding the goal. Find the longest substring where you can replace at most k characters to make every character in it the same. Essentially, it's all about maximizing a uniform run within limited edits. We compared the brute force approach, which checks every possible substring, far too slow, with the sliding window method, which keeps track of character frequencies and adjusts efficiently. This gave us a clean ON solution. Our plan was clear. Use 2 pointers to represent the window, track how often each character appears, and expand or shrink the window based on whether we exceed the allowed number of replacements. Throughout, we keep updating the longest valid window length. We translated this logic step by step, ran it successfully on LeetCode, and the code executed perfectly without any errors. All test cases passed smoothly, confirming that our logic correctly handles everything from uniform strings to shifting mixed patterns. The takeaway? Sliding window mastery is all about control, expanding when you can, contracting when you must, and always keeping track of what matters most. Nail this, and you'll be ready for some of the toughest optimization problems in interviews.